So your service passes every load test in staging. Bravo. The benchmarks on your staging cluster are honestly a little smug. And then you deploy it to production Kubernetes cluster and the mystery begins. The P99 latency spikes for no reason. Throughput comes in 20% under what the staging said it would. And then there's this random restart problem. kubectl describe pod shows last state terminated and reason OOMKilled. The pod does come back up again, runs for few hours and then it does it all over again. And the instinct is to throw more resources at it. Double the memory limit, bump up the CPU request, which the thing is often just papers over the fundamental misalignment between the language and the infrastructure you have wrapped it in. Here's the perception gap, and it's simple once you see it. Go's runtime doesn't naturally perceive the boundaries of a container. When you run a Go binary on bare metal, the runtime looks at the host. It sees all 64 cores. It sees 256 gigs of RAM and it configures itself to use the resources, which is exactly what you'd want on a bare metal. But when you wrap that same binary in a container and set limit of say 2 CPU and 4 gigs of RAM, the runtime often just keeps believing it's running on a 64 core machine. Because from its point of view, it kinda is. And that isn't a theoretical quirk. It's a recipe for two specific kind of silent failures. One on the CPU side and one on the memory side. And the worst part is that neither of them throw a Go panic. Neither of them write a stack trace. And neither of them show up in the place you are actually looking for. Failure mode number 1 is what I call the scheduling storm. It's a CPU problem. So Go's scheduler manages P's, that is capital P, P for processor. Now each P is the ceiling on how many Go routines can actually run the code in parallel. By default, the number of P's is set by the GOMAXPROCS environment variable, which traditionally defaulted to the number of logical CPUs the runtime thinks it has. And there it is, the runtime thinks it has 64. So if Go thinks it has 64 cores, but your Kubernetes CFS quota is restricting you to 2, you end up with a 64 scheduler rings competing for 2 physical CPUs. The result is a massive context switching overhead, cache trashing, and a throughput drop that doesn't show up in your CPU usage graphs. It just shows up as slow. And your CPU usage graph might say you are at 80%, which is comfortable number, and meanwhile the kernel is throttling you for every 20% of every 100 millisecond window because you have exhausted your quota. And somehow this gets even worse. The garbage collector isn't polite about your quotas either. During its concurrent phase, the GC spins up dedicated workers and grabs idle workers of any free P it can find to keep up with the heap growth. On a 64P setup, that's a lot of Go routines all asking for CPU at the same moment on top of whatever your user code is already doing. And the kernel doesn't know the difference. It just sees a quota and it throttles. So even when your application logic is well behaved, a single GC cycle can blow through your CFS window and your P99 starts looking like a seismograph. And the Go runtime, total innocent, just doing its job. Failure mode number 2 is the garbage collection blind spot, and this one is a memory problem. Go's GC is designed to be efficient, but historically it's been oblivious to containers' memory limits. It triggers based on heap growth. There's a Go GC variable. And the Go GC only knows about Go's heap, not the C group ceiling above it. So picture this. Your heap grows from 256 megabytes to 512. The GC looks at Go GC and decides it's not time to run yet and quietly waits, but your container's hard limit is 512. So the Linux kernel doesn't wait for Go to make up its mind. It just steps in with a sick kill and an OOMKill event happens. And the runtime gets killed before it even realizes it was running out of memory. 1 megabyte away from the execution, as they say. And the worst part, and I keep coming back to this, is that Go's point of view, nothing went wrong. There was no panic, no allocation failure, no error return. The process just stopped existing. So your pods restart, runs a few hours, and then does it again. And your alerting is screaming about Kubernetes being flaky when the actual problem is that Go's GC is making scheduling decisions in a parallel universe where memory is infinite. So why do we call this a silent crisis? Because none of the tools you reach for first will tell you what's actually happening. CPU throttling doesn't look like CPU throttling. It looks like a gradual increase in latency. Look at your dashboard and CPU usage only shows 80%, which is true technically, but the most misleading kind of true. And meanwhile, the kernel is throttling you because you burned through your quota for that millisecond window. And the numbers are fine, the user experience is not. OOMKills don't look like OOMKills either. They look like infrastructure instability. Why is the pod restarting, you ask? And the Go runtime was blissfully unaware that it was 1 megabyte away from the execution. You blame the node, you blame the scheduler, you blame whosoever is on the call. And meanwhile, Go is just sitting there making heap decisions completely blind to the C group above it. And the most dangerous part is that the runtime and the kernel both are behaving correctly. Each is doing what it's supposed to do, given the information it has. The bug is that the information doesn't cross the boundary. The good news is that Go has evolved. The bad news is that it has evolved on purpose, which means you have to know what's available. From Go 1.19 onwards, the runtime has introduced safety valves, most notably GOMAXPROCS, which lets you tell the GC, hey, the C group is 512 megs, plan accordingly. And from Go 1.25, GOMAXPROCS is finally C group aware by default. So on a 64-core node with a 2-core quota, you actually get 2 Ps instead of 64. But, and this is the part that gets glossed over in release notes, these ain't magic switches. They require intentional configuration, an understanding on how runtime actually interacts with the kernel, and a willingness to measure instead of guess. GOMAXPROCS in particular is a risk reducer, not a guarantee. It tunes the GC's decision. It doesn't override the kernel's. So over the next 4 episodes, we are going to tear down the black box of Go runtime in containers. We are going to start with GOMAXPROCS, including the fractional CPU trap that bites people running on a sub-core quota. Then GC under pressure with GOMAXPROCS as a centerpiece. Then the real impact of STW pauses when your CPU is being throttled. And then the practical debugging workflow, a checklist, a profiling guide, the kind of thing you actually open at 2 a.m. If you are running Go in production on Kubernetes, you ain't just managing a binary. You're managing a complex interaction between a sophisticated runtime and a restrictive kernel. And the runtime doesn't know about the kernel doesn't know about the runtime, and the gap between those two is where the latency and OOMKills come from. It's time to stop guessing and start tuning. The blog post is linked below. It has series roadmap and the references. Subscribe if you want the rest of the series, and in the comments tell me your worst Go in Kubernetes horror story. I read all of them, and some of them are going to be in the future episodes.